5 minutes I'll do, and you get to go home, is how do I compute this magic weight for each of these samples that I made them to agree with my evidence, but in making them agree with my evidence, I'm taking a risk, and that risk is the weight. Let's do that here. So I start trying to draw an example from here. What I do is for variables which are evidence variables, I don't sample them at all. I just assume they are correct, but then I put the weight. I'll show you how. So I start with the cloudy. So in the beginning, the weight of the example is 1.0. It hasn't yet been computed. So the weight of the example, the sample that you're about to compute is now still 1.0. So then I start sampling cloudy. Okay? And I sampled cloudy, I got true, cloudy to be true. Okay? Now that I have got cloudy to be true, then I have to sample sprinkler, but I don't want to sample sprinkler. I want to agree with sprinkler because that's part of the evidence. I want just sprinkler to be true. I am wishful thinking. How wishful am I? If cloudy is true, sprinkler being true is only 0.10 probability. So I'll go ahead and assume sprinkler is true, but then I have to multiply it by the actual probability, 0.10. So the rest of the sample cannot be one weight, it's at least 0.1 times some weight, because I already took a big risk here. Then I do the rain. Rain I actually sampled and it came true. That's fine. Then I do wet grass, but I don't want to sample wet grass because wet grass is actually in evidence. I want it to be true. But I want it to be true given that sprinkler is true and rain is true. If sprinkler is true and rain is true, wet grass is true with 0.99 probability. So by making wet grass true, I am essentially saying I have to multiply this by 0.99. So at that point I got one sample, cloudy true, sprinkler true, wet grass true, rain true. But that sample has a weight of 0.099. 0.099 is not a big deal, but it's a huge big deal compared to 0. This is the thing that you would have just thrown out the window. But now you at least, like basically, this is partial credit. Right? Think of partial credit. Everybody keeps saying, I did so much stuff. Give me something. That's what I'm saying. So we are looking at, basically how much hallucination you want to do to agree with your, evidence. If your evidence is more or less right with respect to the current sample, you are not hallucinating too much. I won't penalize you. If your evidence is not at all like the current sample, then you are hallucinating a lot. So I'll penalize you with the probability that you are hallucinating. This is called likelihood weighting. Extremely simple improvement over rejection sampling. But it's a way better algorithm. It's a way better algorithm. In fact, it turns out that the idea of likelihood weighting is how you end up doing, inference on things like dynamic Bayes networks, in particular on, hidden Markov models and so on. If you're doing it with sampling, you do likelihood weighting. And I don't know if any of you have heard of a fancy idea called particle filtering, and it's just a variation of likelihood weighting. So all likelihood weighting is doing is, I will let the example be, let Trump be Trump, but what's the cost of Trump being Trump? That's the probability. You multiply it by the probability, that is the likelihood of that particular example. Instead of examples being ones and zeros, they will now, here is an example of 0.099 realisticness, here is an example of, here is a sample of 0.11 realisticness, etc. Now, given these samples, now if you want to answer the query, what percentage of cases is cloudy true? You count the weights of all the samples where cloudy is true, add them up, put it in the denominator. Count all the weights of all the samples, put them in the denominator. That's your probability of cloudy. The thing that you changed between rejection sampling and likelihood weighting is you avoided throwing away samples. And throwing away samples can be a hugely bad thing, especially in things like dynamic Bayes networks, where the evidence is presented way down in the causal order. Because you're going to go in the topological sort order when you are looking at the network. And if the evidence is way down below, you constructed this entire example which gives values to million minus one of the variables, and then when it gives the value to the millionth variable, it says sorry, you didn't agree with what the evidence is saying, out you go. That way, just to get an example, get a sample, you will spend so much extra computation. This one is saying, okay, I understand you went all the way, last part was wrong, but I'll give you partial gradient. Do you see what I'm saying? That is, likelihood weighting. But just sort of think about the fact of how different this kind of algorithms are from the exact algorithms, where you are essentially doing these factors and multiplying the factors, doing computation trees. This one is just coin toss. The part that is actually interesting here, in fact, there is one more idea that I won't talk about today, but I'll tell you next class when we come back, called Markov chain Monte Carlo. And that's called MCMC. That's another thing that you should tell people, then they'll be very impressed. If you go to any data science companies, you should sort of say, MCMC in the middle somewhere, and your chances of getting the job will increase. So I'll tell you when to say MCMC, when we start next class. That is one more slight, even better improvement on likelihood weighting. And it actually uses Markov blanket to essentially look at a state of the entire network. Given the state of the entire network, there is a chain which tells you the next state of the entire network, and then next state of the entire network. It's a Markov chain, and those of you who know Markov chains know that under certain conditions, Markov chains will have stationary distributions. What Markov chain Monte Carlo does is it computes the stationary distribution of the Markov chain underlying. Okay, and once it has the stationary distribution, it can compute all the probability very easily. But that's a little more complex, and it will kill me if I try to explain it to you. But notice something. So one thing that you may want to think about is how come there are no sampling-based algorithms for logical inference? It's a very easy answer, but this is something that somehow probability seems to have free. Okay, probabilistic reasoning you can get by with samples. And then one other thing that I actually mentioned is to realize that you are not sampling the real world. You're sampling the network. Understand the distinction between them. You really, really need to understand the distinction. Sampling the real world would mean setting up experiments. Sampling the networks would mean tossing a fake coin. World of difference. Okay, thanks for coming. We'll see you Friday after.